Hello, all. Today, I want to spend a little time working on the Hugging Face tutorial, and I'm not at the beginning of it, so we're kind of jumping in. I guess this is chapter two uh, or lesson two. So, uh, what I'm hoping uh, is that maybe you'll learn some techniques that will make using these tutorials a little easier. Uh, Anyways, it gives me an opportunity to just fool around, and uh, I guess it makes it more interesting for me to do a recording while I'm going through this. So anyway, I'm going to jump over to the desktop and we can get started with this. So I have this set up now side by side with a Jupyter notebook, and if you'd like to see how I set up my Jupyter lab, uh, just make a comment and I can do that for you. Uh, so one of the things here is that there are some videos for this, but I find that I do better when I read the information below, and because I have a little bit of trouble with strong accents. Because my hearing is not as good as it used to be, it makes it more difficult. And so what I do instead is I come up here to my assistive technology here, my accessibility shortcuts, and go into the preferences, spoken content, and speak items under the pointer. And I can use a voice that is easy for me to understand. You can select your voices here. These are kind of old voices. These Siri voices are the newer voices. If you don't have Siri Voice 4, you can hit the customize and it will help you to download additional voices. So that's the one I've chosen, and it sounds like this.
I'm Siri.
And so anyway, once this is turned on here, uh, it doesn't seem to work immediately. You actually have to highlight the first bit of it and do a option escape.
And we'll take a closer look at creating and using a model. We'll use the auto model class, which is handy when you want to instantiate any model from a checkpoint.
All right, so that's what we want to do. We want to instantiate a model from a checkpoint. So we're going to get there. Now, why isn't this working? Well, I just highlight it here and Alt escape it again.
A model class and all of its relatives are actually simple wrappers over the wide variety of models available in the library. It's a clever wrapper as it can automatically guess the appropriate model architecture for your checkpoint, and then instantiates a model with this architecture.
Well, the pointing thing doesn't seem to be working right now, but that's probably fine because this way I can control it a little better, and I'm going to want to talk over it anyway. Uh, so I guess the point they're trying to make here is that there's a whole library that's available for doing pre-processing on a model, uh, and then or pre-processing on training data or data that you want to use for inference. And then there's the actual model itself that it goes through, and then there's post-processing that happens. And there are wrappers that can help with all of this. The wrapper that helps the most is the pipeline wrapper, but that also is not as flexible, I guess, as some of the other wrappers. And the auto model class is another wrapper. So let's go about creating a transformer here. And so what you can do is you can hit these little code excerpt icon here, and it says copied, and come over here. And if I right click on this, this is the thing that I dislike about, if I hit paste cells here, nothing happens. This is something I dislike about Jupyter. If I want to paste, I've got to use the keyboard for that and do a Command V, and then it pastes fine. And then if I hold the shift down and hit enter, it will run that cell. And if you look down here, if you look down quickly, it said busy for a couple of seconds, and now it says idle. So you can always check down here to see if your cell is still running. And then, of course, it comes back with a number here that should tell you that it's finished. It's finished running. And if you don't like the shift enter, you can change it here to execute with enter. But I find that shift enter is just seems a little safer. That it's not that hard to do that, and it keeps me from making errors, I think. And so what we can do here is we can print this config now. And in the Jupyter Notebook, you don't actually have to say print config, you just say config, and then shift enter, and there it is. And so this is a configuration file that gets downloaded that sets a lot of hyperparameters. So you need to know things like the hidden size, because when we do the pre-processing, we have to make the input to that size. Anyway, we don't need to keep this around. I can hit this little trash can. You don't get these icons in Jupyter Notebooks, I don't believe, but you get them in Jupyter Lab, at least this version of the Jupyter Lab. So I kind of like that, because then you don't have to remember some of the keystrokes. I always forget. I think you do a DD, just like a Vim command. If I do a DD, I think, yeah, that'll delete it. But these little icons are helpful. And then you can also print the model. If I want to add a cell below, I can hit this. And take a look at the model also. And we can see it has this dimension of 768 in the first layer, and then all of the different layers are in here, and you can look through this and see what they are. And when you're done, you can trash it because we don't need it. Why do I have two of these in here? I don't need two of these. All right, so let's highlight this and Option Escape.
You haven't seen what all of these attributes do yet. You should recognize some of them. The hidden size attribute defines the size of the hidden states vector, and num hidden layers defines the number of layers the transformer model has. Creating a model from the default configuration initializes it with random values.
All right, so yeah, if we make a model now, we don't really have good values in it. So let's see if what we can do. Well, this is the same thing again. I don't know why they put this in two places. We don't need this. Let's put this in the trash. Or maybe we'll keep this one and trash this one here. Let's leave the comments in here. Don't know that we need them, but I like this comment here.
Can be used in this state, but it will output gibberish. It needs to be trained first. We could train the model from scratch on the task at hand, but as you saw in Chapter 1, this would require a long time, and a lot of data, and it would have a non-negligible environmental impact. To avoid unnecessary and duplicated effort, it's imperative to be able to share and reuse models that have already been trained. Loading a transformer model that is already trained is simple. We can do this using the from pre-trained method.
All right, I'm just going to copy it this way. I'm not going to copy this again. What's the point? Let's go into here and let's do this. And this thing here is all right, so what is this called? This is called a checkpoint. So a checkpoint is going to be the weights, all of the weights from the trained model. So BERT model is the architecture that's used, and BERT base case is the checkpoint. So now let's go ahead and run this, hold shift down and hit enter. Let's see down here. So this one here we did not need. Let's do this again. Because here is where we're doing it with the checkpoint. All right, so let's see what this says here.
Weights of the model checkpoint at BERT base case were not used when initializing BERT model. CLS predictions bias. CLS predictions transform layer norm bias. CLS predictions transform layer norm weight. CLS the following relationship bias. CLS predictions transform dense weight. CLS predictions transform dense bias. CLS predictions decoder weight. CLS the following relationship weight. This is expected if you are initializing BERT model from the checkpoint of a model trained on another task or with another architecture, e.g. initializing a BERT for sequence classification model from a BERT for pre-training model. This is not expected if you are initializing BERT model from the checkpoint of a model that you expect to be exactly identical. Initializing a BERT for sequence classification model from a BERT for sequence classification model.
I'm not really sure what's going on there. I guess maybe we don't need this here. Maybe this has configuration information in here that is not the same as what we see in BERT base case. So let's get rid of this configuration file and run it again. Shift enter. And we're getting the same thing back. But I don't think that we need to pull down the config file because when we import the BERT model, we get the config file automatically. But this is part of the flexibility of the API, that if you want to grab BERT config and use BERT config, you can. So let me just highlight this.
Saw earlier, we could replace BERT model with the equivalent auto model class. We'll do this from now on, as this produces checkpoint agnostic code. If your code works for one checkpoint, it should work seamlessly with another. This applies even if the architecture is different, as long as the checkpoint was trained for a similar task, for example, a sentiment analysis task. In the code sample above, we didn't use BERT config, and instead loaded a pre-trained model via the BERT base case identifier. This is a model checkpoint that was trained by the authors of BERT themselves. You can find more details about it in its model card. This model is now initialized with all the weights of the checkpoint. It can be used directly for inference on the tasks it was trained on, and it can also be fine-tuned on a new task. By training with pre-trained weights rather than from scratch, we can quickly achieve good results.
Now, I don't know exactly what BERT base case was trained for, but we could go to Hugging Face and look at the model card, and it would tell us what it was trained for, what tasks. And so then we would use it correctly. They'll probably tell us. So, options
Have been downloaded and cached, so future calls to the from pre-trained method won't re-download them in the cache folder, which defaults to .cache Huggingface Transformers. You can customize your cache folder by setting the HF home environment variable. The identifier used to load the model can be the identifier of any model on the model hub, as long as it is compatible with the BERT architecture. The entire list of available BERT checkpoints can be found here.
By the way, in one of my previous videos, I talked about this .cache directory, Hugging Face Transformers. This is where models get stored. And if you start working with a lot of models, you're going to find that you're going to be running out of disk space eventually. So you can go in here and you can start deleting models. It's a good idea to empty that out every once in a while. It doesn't take that long to re-download them when you need to use them. Unfortunately, the names of these files are such that you can't tell what model is which file, so it makes it difficult to curate them. One of the things that you can do is you can use the HF, where is it here? The HF under home environment variable. You can use that for models you want to keep permanently. You can set this when you're downloading them, and then they'll go into a different location. And then when you're just testing, you can use this location so you know you can clean it out. You just have to remember to reset the HF home environment variable. You can always do that with a wrapper. And also there's some pip modules that will handle that for you. When you're in a certain directory, you'll get certain environment variables. Off the top of my head, I don't remember the names of them, but it can be done. And so that's something that you may want to look into. It can also immediately change into the correct conda environment for you when you're in a particular directory. But I don't have that installed right now, and the last time I tried to install it, I had some difficulties. So maybe it's a Mac thing. I didn't have any trouble installing it on Linux. But we're getting off point here. Let's go back. So yeah, this I guess will take us to the model zoo, and we could look at all those different checkpoints that can be used. And then we can save this. I guess this is another way to handle that same thing here. We can paste this in here. And see, once again, you can't use the right click. It drives me crazy. This. And I can just make this tilde models. I think I already have a models directory. Shift enter here. So I think that the directory probably has to exist, but I'm not sure about that. So if you have trouble, that's probably the reason. If you try to save it someplace that doesn't exist. But this seemed to work fine. So now we can do this. Now, if you're in a Jupyter notebook and you want to do an operating system command, you have to put a bang in front of it. That's an exclamation point. In computer science, we call this a bang. So we do an ls of the tilde. Tilde stands for the home directory. And then once again, it's shift enter, not just enter. I thought I had a models directory. Oh, it's capital M. So well, this doesn't make much sense because I just saw that I have a models directory here. Users barred code models. There we go. Code was also capitalized. All right, I don't know why this didn't save here. Does this need... Well, let's do it like this. Let's see what happens. It's possible that it does not like the tilde. Well, that worked. So I don't know where this saved it. I didn't save it in my... well, let's see. Bang, CD. Uh, looks as though my Vim commands are not working. So it made it in my in the directory I was in when I started up the Jupyter notebook. Keep trying until I get one that works. There we go. And now, all right, back in the right place, and let's get rid of these guys here. Don't need them, don't want them. There we go. All right, so this is one of these little icons are really great. You will get this in a Jupyter notebook, but you will get it in Jupyter Labs. And that's why I like to run Jupyter. One of the reasons I like to run Jupyter Labs. There are a lot more features in here, including this dark mode, which is really great. It's got this Jupyter Lab dark. It's got a lot of features in here that make it a more pleasant experience, in my opinion. And so, if we do this, yeah, did we see two files? I don't remember. We should see. Yeah, this is not going to run like this. Needs the bang. Yeah, it's got the two files. That's fine.
Take a look at the configuration file. You'll recognize the attributes necessary to build the model architecture. This file also contains some metadata, such as where the checkpoint originated and what smiling face with smiling eyes and hugging hands Transformers version you were using when you last saved the checkpoint.
And this should look a lot like the config we looked at earlier. It's the same hidden size. So it has the number of attention heads and a lot of other information in here. But for one thing, you'll see this configuration is a lot smaller than the one that we looked at before. And it looks like it's less complex than the one we looked at before. So it is different. And I believe that, you want to use the same preprocessor and the post-processor and whatnot that go along with with this configuration. The configurations have to match up, I believe. So we don't need to see this anymore. Get rid of it.
Torch model bin file is known as the state dictionary. It contains all your model's weights. The two files go hand in hand. The configuration is necessary to know your model's architecture. while the model weights are your model's parameters.
So this is this .bin file. This is the large file with all the weights. So they can get out of control. I guess one of the things that I'm seeing here is that if we save the file to a local directory, then we should be able to manage that .cache directory better, because that can get out of control pretty quickly. And I guess the important thing here is that we remember that this is known as the state dictionary, so that when we see this term later on, we won't get confused.
You know how to load and save a model. Let's try using it to make some predictions. Transformer models can only process numbers that the tokenizer generates. But before we discuss tokenizers, let's explore what inputs the model accepts. Tokenizers can take care of casting the inputs to the appropriate framework's tensors. But to help you understand what's going on, we'll take a quick look at what must be done before sending the inputs to the model.
All right, let's say we have a couple of sequences. The tokenizer converts these to vocabulary indices, which are typically called input IDs. Input IDs. It's another important term. Each sequence is now a list of numbers. So we have this big, I think they call it a bag of words, big bag of words here. I think the BERT models have something like 26,000 words in their vocabulary, and each one has a number, and those are input IDs. All right, so when we tokenize, it converts these vocabulary indices, which are typically called input IDs. Each sequence is now a list of numbers. The resulting output is blah, blah, blah. This is a list of encoded sequences, a list of lists. So here's a list. Here's a list. Here's a list. You'll see that they all start with 101, all end with 102. And that's because this is the start token, this is the end token. And so the two tokens in the center here are what are used to place these words are defined by a vector, and this is these two tokens make up that vector. So if you think of a two-dimensional space that's mapped for words that are close in meaning should be close to each other in the vector. So here we have two words that share this 9999, and that is hello and nice. And so I guess maybe this is this could stand for something like positive. And that's I wouldn't call that a guess. It's just a sort of maybe a metaphor for what's going on. So tensors only accept rectangular shape. Think matrices. This array is already a rectangular shape, so converting it to a tensor is easy. So we're going to do this here. Well, we better run this one here at once. This. It's going to use this, so I better do it. I mean, normally, we would use a preprocessor to get the encoded sequences. Here, we're just entering them in ourselves. Excuse me. Here, we're just entering them in ourselves, which is something we'll probably never do again. Anyway, let's copy this, paste this in here. Always do that. All right, so now we have model inputs. We can take a look at those. And so this has turned this list of lists into a tensor. And I guess this is a PyTorch tensor. Because when I set up this course, I told the system that I was using PyTorch and not TensorFlow. So this tensor is for PyTorch. Of course, this would tell you that too. Import torch up here. All right, so now we're going to generate output here. And it's pretty self-explanatory. Always right-click this thing. If anybody knows how to add paste into Jupyter Notebook's right-click menu, just simple paste, please leave it in the comments because it's maddening. All right, and now we can just print out output. So this is one of the nice things about using a Jupyter Notebook is that it makes it easier to rerun code, and also you don't have to type print every time. So here we go. This is what was generated when we went through the model here. And of course, I don't understand what any of this is because these are all tensors, and in order to take a look at what these are, we have to convert them from tensors back into words. All right, so let's see what this says here. And
Model accepts a lot of different arguments. Only the input IDs are necessary. We'll explain what the other arguments do, and when they are required later. But first we need to take a closer look at the tokenizers that build the inputs that a transformer model can understand.
so we skipped that step here. We just, rather than running this sequence, these sequences through a tokenizer, we just made a list of lists here. So the tokenizer should produce this encoded sequence, these encoded sequences for us. All right. It's going to be a very long video because I'm just going through this tutorial. So if you haven't gone through any of this before, you might want to go back to the very beginning of the tutorial, and once you get through the first part, you start to see stuff that you've seen here. Come back and watch the rest of this. So I'm trying to get this to show the whole URL here. So yeah, this is it here. Huggingface CO/course will get you there. And then this guy's a little easier for me to understand, but I still have trouble because he has a French accent, and so he pronounces things differently. And because my hearing is poor, I have a little bit of trouble. Uh, they've done very good jobs on these videos, so I would recommend that you do watch them. I just have trouble with them.
Tokenizers are one of the core components of the NLP pipeline. They serve one purpose: to translate text into data that can be processed by the model. Models can only process numbers, so tokenizers need to convert our text inputs to numerical data. In this section, we'll explore exactly what happens in the tokenization pipeline. In NLP tasks, the data that is generally processed is raw text. Here's an example of such text.
All right. I'm not sure where we're copying this, but it's got a little copy button here. All right.
However, models can only process numbers, so we need to find a way to convert the raw text to numbers. That's what the tokenizers do. And there are a lot of ways to go about this. The goal is to find the most meaningful representation. That is, the one that makes the most sense to the model. And if possible, the smallest representation. Let's take a look at some examples of tokenization algorithms and try to answer some of the questions you may have about tokenization.
So when something is tokenized, it can be tokenized in a lot of ways, and a lot of information can be given, but that actually would slow things down. So they're saying here, we're trying to get the smallest representation from tokenization that does a good job without slowing things down too much, using too many compute resources. So here's another video, and yeah, go ahead and watch that. And I mean, the good thing about these videos is that what's written down here is pretty much what they say in the videos.
This type of tokenizer that comes to mind is word-based. It's generally very easy to set up and use with only a few rules, and it often yields decent results. For example, in the image below, the goal is to split the raw text into words and find a numerical representation for each of them. There are different ways to split the text. For example, we could use whitespace to tokenize the text into words by applying Python's split function.
All right, so we can run this. What's going on up here? So this is pretty self-explanatory. It's created a list with 1, 2, 3, 4, 5 words.
Also variations of word tokenizers that have extra rules for punctuation. With this kind of tokenizer, we can end up with some pretty large vocabularies, where a vocabulary is defined by the total number of independent tokens that we have in our corpus. Each word gets assigned an ID, starting from 0 and going up to the size of the vocabulary. The The model uses these IDs to identify each word.
You can think of the ID as being an index from 0 to n. And then, of course, the index has, it has a data payload, which is the word itself, and then the embedding for it. So when we or the encoding for it. So that would be this 101 through 102 would be the encoding for the word hello.
Want to completely cover a language with a word-based tokenizer? We'll need to have an identifier for each word in the language, which will generate a huge amount of tokens. For example, there are over 500,000 words in the English language, so to build a map from each word to an input ID, we'd need to keep track of that many IDs. Furthermore, words like dog are represented differently from words like dogs, and the model will initially have no way of knowing that dog and dogs are similar. It will identify the two words as unrelated. The same applies to other similar words, like run and running, which the model will not see as being similar initially. Finally, we need a custom token to represent words that are not in our vocabulary. This is known as the unknown token, often represented as uncor. It's generally a bad sign if you see that the tokenizer is producing a lot of these tokens, as it wasn't able to retrieve a sensible representation of a word and you're losing information along the way. The goal when crafting the vocabulary is to do it in such a way that the tokenizer tokenizes as few words as possible into the unknown token. Amount of unknown tokens is to go one level deeper, using a character-based tokenizer. Character-based tokenizers split the text into characters, rather than words. This has two primary benefits. The vocabulary is much smaller. There are much fewer out of vocabulary, unknown tokens, since every word can be built from characters. But here too some questions arise concerning spaces and punctuation. This approach isn't perfect either, since the representation is now based on characters rather than words. One could argue that, intuitively, it's less meaningful. Each character doesn't mean a lot on its own, whereas that is the case with words. However, this again differs according to the language. In Chinese, for example, each character carries more information than a character in a Latin language. Another thing to consider is that we'll end up with a very large amount of tokens to be processed by our model, whereas a word would only be a single token with a word-based tokenizer. It can easily turn into 10 or more tokens when converted into characters. To get the best of both worlds, we can use a third technique that combines the two approaches: subword tokenization. Subword tokenization algorithms rely on the principle that frequently used words should not be split into smaller subwords, but rare words should be decomposed into meaningful subwords. For instance, annoyingly might be considered a rare word, and could be decomposed into annoying and lie. These are both likely to appear more frequently as standalone subwords, while at the same time the meaning of annoyingly is kept by the composite meaning of annoying and lie. Here is an example showing how a subword tokenization algorithm would tokenize the sequence. Let's do tokenization.
So we see token and ization are broken up in two parts because ization is used in a lot of words. So this has a meaning and token has a meaning. So this, if it was tokens, you have token here and the S over here, which would, pluralize it. Uh, and this is a very efficient way of doing it. It's called lemmatization. Uh, and I think this is how most models work. Oops.
Subwords end up providing a lot of semantic meaning. For instance, in the example above, tokenization was split into tokenization, two tokens that have a semantic meaning while being space efficient. Only two tokens are needed to represent a long word. This allows us to have relatively good coverage with small vocabularies and close to no unknown tokens. This approach is especially useful in agglutinative languages such as Turkish, where you can form almost arbitrarily long complex words by stringing together subwords. And more. Unsurprisingly, there are many more techniques out there. To name a few, byte level BPE, as used in GPT-2, word piece, as used in BERT, sentence piece or unigram, as used in several multilingual models. You should now have sufficient knowledge of how tokenizers work to get started with the API. Loading and saving. Loading and saving tokenizers is as simple as it is with models. Actually, it's based on the same two methods from pretrained and save pretrained. These methods will load or save the algorithm used by the tokenizer, a bit like the architecture of the model as well as its vocabulary, a bit like the weights of the model. Loading the BERT tokenizer trained with the same checkpoint as BERT is done the same way as loading the model, except we use the BERT tokenizer class, S.
All right, so let's give this a try. All right, I'm not really sure why this is printing out. Ah, yeah, I can't tell you why this is printing this out.
Similar to auto model, the auto tokenizer class will grab the proper tokenizer class in the library based on the checkpoint name, and can be used directly with any checkpoint.
All right, so you see here, we put the same checkpoint in here that we used up above here for base cased. So when we created the model, we use this checkpoint. When we create the tokenizer, so this is a tokenizer object, it's object-oriented programming. So we use the same checkpoint, and it's going to grab the correct one. What's going on here? It's the same functions. So I guess what this is saying here is what? All right, so here we specified that we wanted BERT Tokenizer. If we don't remember the syntax for this, we can do it this way. I think this gives you the exact same result, but from a different syntax. So I guess I'm not completely understanding what this uh, auto star prefix is doing here. Not really sure what the advantages of using auto model and auto tokenizer classes. Maybe it makes the code a little easier. Maybe we can put a variable in here and then set the variable up above, and then it can work on whatever checkpoint we want. Whereas if we use this in here, this would also have to come from a variable. I don't even know if that's easily done in Python. So I guess from a coding point of view, if you want to do different kinds of testing, then this auto star methodology makes a lot of sense. There may be other reasons for using it, but I can't think of them right now. So now that we have a tokenizer that we created, we can use it. And so input IDs is, I guess, a dictionary. I thought when we did this before that we got input IDs. It looks as though I'm a little bit confused here. We're getting a dictionary here that has an entry called input IDs. This is the key, and the value for it is this list here of let's see what we have. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. So it looks as though the input IDs is just the indices, the IDs, what was called IDs before. In other words, it's not the encodings. It's just that bag of word ideas where each word in the vocabulary is numbered. And then down here we have another key, token type IDs, and they're all set to 0. And I'm not sure what that is. And then an attention mask, which means that all of these are turned on. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 items up here. if we count the start and stop tokens. So, yeah, these are just tokenized, but they're not encoded yet. Let's see. And now we can save this also. There I go, right-clicking again. And so these are the things that were saved: the tokenizer config.json, the special tokens map.json, the vocab .text, add tokens, and so on. And later on, I'll take a look at each one of these files. We'll talk more about token type IDs in Chapter 3. We'll explain the attention mask key a little later. First, let's see how the input IDs are generated. To do this, we'll look at the intermediate methods of the tokenizer.
Translating text to numbers is known as encoding. Encoding is done in a two-step process, the tokenization, followed by the conversion to input IDs. As we've seen, the first step is to split the text into words, or parts of words, punctuation symbols, etc., usually called tokens. There are multiple rules that can govern that process, which is why we need to instantiate the tokenizer using the name of the model, to make sure we use the same rules that were used when the model was pre-trained.
I made a mistake before. So this is the start and the end token, but then we have 1, 2, 3, 4, 5, 6. No, I didn't. I thought there's no period here. So it's not punctuation. One of these words was broken into two parts.
Second step is to convert those tokens into numbers, so we can build a tensor out of them and feed them to the model. To do this, the tokenizer has a vocabulary, which is the part we download when we instantiate it with a from pre-trained method. Again, we need to use the same vocabulary used when the model was pre-trained.
And I don't want that first guy here. Symbol here, pipe. All right, I had a little trouble here for some reason. This should work. So I better do 100 here. Well, that's no good if everything's unused. 1,000. All right, here we go. So here are all the different tokens in the vocabulary. Right? Uh, like this. it's nice that you can do all of these kinds of things inside of a Jupyter notebook or Jupyter Lab.
Second step is to convert those tokens into numbers, so we can build a tensor out of them and feed them to the model. To do this, the Tokenizer has a vocabulary, which is the part we download when we instantiate it with the from pretrained method. Again, we need to use the same vocabulary used when the model was pretrained. To get a better understanding of the two steps, we'll explore them separately. Note that we will use some methods that perform parts of the tokenization pipeline separately to show you the intermediate results of those steps. But in practice, you should call the tokenizer directly on your inputs, as shown in the section 2, Tokenization. The tokenization process is done by the tokenize method of the tokenizer.
Right. All right, so here we can see that Transformer was indeed broken into two pieces when it was tokenized. And that's why we had one more token than we had words. Actually, three more tokens because we have the stop and end.
Tokenizer is a subword tokenizer. It splits the words until it obtains tokens that can be represented by its vocabulary. That's the case here with Transformer, which is split into two tokens, transform and er. From tokens to input IDs. The conversion to input IDs is handled by the convert tokens to IDs tokenizer method.
Okay, so there are our IDs, and I guess if we're going to go down to 170 lines in our vocabulary, we're going to find the word using, and this, wait a second, maybe this is using a, let's count these, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7. So this does not include the begin token and the end token. So this is using, and this is A. So if we went to line 170 in our vocabulary, it would be the word A. We went to 13809, it would be trans. And then we see here, we're still not ready.
Outputs, once converted to the appropriate framework tensor, can then be used as inputs to a model, as seen earlier in this chapter.
So we can't use them directly like this. We have to convert them first into a PyTorch tensor. We'll skip that part for now.
Decoding is going the other way around. From vocabulary indices, we want to get a string. This can be done with the decode method as follows.
So here we actually put the list in here of our tokens. But what I'm wondering is, can we do this? I'm guessing this should work too. Coded like this. Save a little typing. So that works also. So I'm reading this to myself here. I should be doing this because people may be watching.
That the decode method not only converts the indices back to tokens, but also groups together the tokens that were part of the same words to produce a readable sentence. This behavior will be extremely useful when we use models that predict new text, either text generated from a prompt or for sequence-to-sequence problems like translation or summarization. By now you should understand the atomic operations a tokenizer can handle: tokenization, conversion to IDs, and converting IDs back to a string. However, we've just scraped the tip of the iceberg. In the following section, we'll take our approach to its limits and take a look at how to overcome them.
Right, so I'm going to stop the video here. There are a couple of things I need to do, and I'll pick this up later on today. Let's see. Go back to my Streamlabs desktop here. And I hope you found that interesting. This really is an excellent course, and don't skip the first part. The first part is fascinating. This I've read the paper "Attention Is All You Need," and I've been trying to understand transformers for at least a year, and I found the paper to be really unsatisfying. This course, however, goes into doesn't go into great detail about what's going on in transformers, but it explains the fundamentals of them, of what's actually going on, how they're working, what they're doing. So, to me, the lectures about transformers here have given me real intuition, real understanding of what is happening in transformers, how they're working, that I did not get from listening to other lectures, reading papers about transformers. So these guys really understand the technology, and so they are able to explain it. When your teacher really understands what's going on, then the lectures make sense. When your teacher doesn't, you're left confused. Now, I'm sure that the author of the paper "Attention Is All You Need" really understands it very well, but engineers don't often communicate particularly well. No offense, but uh, he's talking to a particular crowd of, I guess, PhDs in the field. And I'm not a PhD in the field, but I'm fascinated by it and just want to learn more at my own pace and not in an academic setting. And I believe there are a lot of people out there like me who want to do this, in their own way. And so finding people who can explain these concepts simply, uh, it's just wonderful. And these guys are able to do this. The other uh, great teacher, I believe, is Jan LeCun, who, if you take his course, you will understand a lot of things also, because he understands them so well that he and Alfredo, his uh, the person running the course, uh, they just understand the concepts so well that they can explain them simply in a way that people can understand them. Anyway, that's about it. I hope you enjoyed this, got something out of it. Please like and subscribe. I really like it when people leave comments, so if you leave a comment, that'll be really great. Thank you for watching.